to the theory of probability. So we will continue our discussion on joint random variables, okay, or jointly distributed random variables. So where we ended last time, we ended at the fact by showing that the sum of so if x and y are two normally distributed random variables, say that x is normally distributed with mean mu x and variance sigma x square, and y is normally distributed with say me and mu y and variance sigma y square, then the sum would be normally distributed with mean mu x plus mu y, in other words the sum of the means, and the variance as the sum of the variances actually. Okay, so this is what the fact that we ended our discussion last time, and we will continue our discussion from here. So what we are going to do in today's discussion, by the way, before moving towards the fact that what we are going to do in today's discussion is we are going to here's a little thing for you. I would suggest actually that there are some other kind of random variables whose sums has been discussed. So for example, if x and y are binomially distributed, okay, distributed random variables, then what would be the distribution of x plus y? Okay, so please keep this as an exercise actually. So read it for yourself. I mean, if you want to read it explicitly, it's on page 260 of the book actually. Okay, so it's on page 260 of Ross actually. So I would suggest that you should do this. And the same is the case that if x and y are say geometrically distributed, okay, and they are independent, then what would be the distribution of x plus y? Okay, so these are the two examples that you should do for yourself actually. And same is the case, say for example, for the Poisson actually, that if the two random variables has a Poisson distribution, okay, with the different parameters, what would be the distribution of the sum of the two Poisson random variables actually? So in a sense, in our last discussion we discussed it's converse actually, that if x plus y is Poisson distributed, then x and y is going to have a Poisson distribution where x and y are independent actually. So I would suggest that read these for yourself. You can find this stuff in section 3.4 and section 3.5 from the book actually. So this is something that you should at least go through once. So what is today's agenda? In today's discussion, we are going to cover some stuff on conditional joint distributions, okay, in both cases discrete and continuous. Okay, we'll consider different examples. And the next thing that we're going to cover in our today's discussion is going to be that if you have a joint of say two random variables x and y, the distribution of say joint distribution of two random variables x and y, and if I have a function of x and y, say let's call this function g, then what would be the distribution, okay, then what would be the distribution of this functions of x, y actually. Okay. So this is really like what you did in one-dimensional case. Actually, there you had a formula that if you know the distribution of the random variable x, you can also compute the distribution of any continuous function or any function of x that is invertible actually. Okay, so we did this in one dimension. Now we want to do in second dimension, that if you know the joint PDF of x and y, then can I find the joint PDF of, say, functions of x and y actually? The answer is that yes, we can do it. And then probably we will end our discussion on what do you call so-called moment generating functions. Okay, moment generating functions, and we'll prove some inequalities like Markov and Chebyshev inequality. Okay, so Chebyshev inequality. So these are the kind of things that we're going to cover mostly in today's discussion actually. So let's just start with the conditional distribution, and the first thing that you should be asking actually is that, okay, as for x and y, you have what you call a joint PDF. So do you have a kind of a notion of a, say, joint conditional PDF actually? The answer is yes. So we will start by defining the joint conditional PDF for the discrete cases when the two random variables are discrete, and then we will do some examples for the continuous case actually. So suppose, so let's start with conditional distributions, but in discrete case actually. Okay, so this is what that we're going to do. So suppose x and y are some discrete random variables. Okay, let x and y are to be discrete. Okay, and then what I would like to define actually, obviously they're going to take some values x and y, discrete values, x and y are going to take some discrete values. Then let me define what do you call the conditional PDF. Maybe the basic question that you can ask is that, can we compute the probability that x going to take the value small x while it is known that y has taken the value y actually? Okay, can we compute this probability? Let's give this probability a name. So this probability is basically the conditional distribution of x given y. So it's a conditional distribution of x given y. So I'm going to denote such conditional distribution of x given y. So the probability distribution of x given y, for the notation that I'm going to use is this x given y. So this is the notation. So what does this notation mean? That what is the probability that x takes the value x given that y takes the value y actually. Okay. Now through our standard, what do you call, definition of conditional expectation and conditional probability, so this is going to be, what do you call, probability of x equal to probability of y. In other words, the probability of intersection. So if you have a given b, it's going to be probability of a intersection b divided by the probability of y equal to y actually. Okay, but what is this? Can I rewrite this expression in a more concrete form? So the probability that x is x and y is y is really the joint PDF of x and y. In other words, that this probability, we know that it's a joint PDF of x and y, divided by what is probability y. We know that for the probability of y, we can say that it's okay. So I can keep it as it is. Okay, so this is really what you call the value of the, say, marginal PDF evaluated at y actually. Okay, so the joint PDF of x and y divided by the marginal PDF evaluated at y is the meaning of the conditional probability when x is x given y is y. Similarly, you can also compute what do you call probability of y given x, okay, which means that probability that y is y given that we know that x is x actually, okay, and this can be again by the same calculation, equal to joint PDF divided by the marginal PDF of x evaluated at simple x actually. Okay. So these two are the formulas, explicit formulas, okay, to compute the what do we call the conditional probability distribution actually. So you can call them as the conditional probability distribution. Okay. So this is conditional. These are, you can call it, that's a conditional PDF actually. Okay. This is conditional PDF. Now, if you have conditional PDF, it is natural to also have conditional CDF actually. Okay. Let's denote that conditional CDF as, say, f, the CDF of x given y evaluated at when x is x or x is less than or equal to x given that y is y. So this is a notation which means that what is the probability that x is less than or equal to x given y is y. Now we know that x is a discrete random variable, so it takes discrete set of values. So this probability can be computed as the sum, okay, of the probabilities over the case when a is, for all values when a is less than or equal to x, okay, and the conditional PDF evaluated at a given x actually. Or maybe if I write it more explicitly, I can say that this is same as that you take the sum over all a's that are less than or equal to x, the all values of the random variable x that, you know, all values a that random variable x takes, which are less than or equal to x, and the probability x equal to a given y equal to y. And what would be this? So you can write this as, what do you call, the conditional PDF, sum of the conditional PDF evaluated at a given y. So this is what is really the definition of the conditional CDF is. So this is conditional CDF. Okay. So now you can also say that what will happen if you can deduce it actually easily from here. So you can pose a question, what if x and y are independent? X and y are independent actually. Okay? So if they are independent, then the conditional PDF of x given y should be equal to this by this. But since x and y are now independent, this is equal to what you call the marginal PDF of x multiplied by the marginal PDF of y, and everything divided by the marginal PDF of y, which is equal to the marginal PDF of x. Okay, so if x and y are two independent random variables, then the conditional probability, the conditional PDF of x given y is simply the PDF of x actually, because y adds no information into it. Okay, so these are some of the basic facts about it. Now let's do what? Let's do some examples. Let's compute what do you call the conditional PDFs. So the first example that I would like to take is that if imagine you have two independent Poisson random variables, okay, and so here's an example. So imagine x is a Poisson random variable with a variant with parameter lambda 1, and y is a Poisson random variable with parameter lambda 2. Okay, so we need to compute the conditional. So we need to compute the conditional probability. Okay, or maybe if I write it explicitly, what is the conditional probability that x is going to be k given that the sum of these two random variables is n actually. Okay. You may also interpret it, say for example, from the point of view of what you call the post office example that we had previously. So imagine this is post office. Okay. And x represents the number of mails that visit the post office on a given day, and y represents the number of females that visit the post office on a given day. Now imagine, given that the total number of the people who have visited the post office on a given day is n. What is the probability that the number of males out of these n are equal to k? Okay. So what is the probability that the number of men are the number of males that have visited post office in a given day is equal to k, given that the total number of people who visited the post office on the same given day is n. So this is the probability, for example, that I'm interested in. How can I compute it? You know, the trick could be that, okay, let's write, say, probability of x given k. By the way, we have an assumption that both are independent. Okay, so the number of males and number of females that visit on a given day post office are independent from each other actually. Okay, so what is the probability that x is, say, k, and x plus y is n actually? Okay, given that what is the probability that x plus y is n actually? Okay, this is what the case is. Now I can rewrite this as, if I think carefully about it, that if the number of males are k on that given day and the total number of people are n, that means that the number of males should be n minus x, but x is k actually. Okay, so in other words, since x is k, so the y would be n minus k actually, given and divided by the probability of x plus y equal to n. Okay. Now what we know about the sum of the independent random variables when you will, do the exercises that what would be the sum of two, what do you call independent Poisson random variables. What you're going to see is that if x and y are Poisson and independent with parameters lambda 1 and lambda 2, then x plus y is also Poisson with parameter lambda 1 plus lambda 2. In other words, they are both average actually. Okay? And now, since all these two are independent, so I can rewrite this probability as probability of x equal to k times probability that y equal to n minus k, given that the probability x plus y equal to n. Now we know that these probabilities explicitly because we know the distribution of x, we know the distribution of y, we know the distribution of sum of x and y. So the answer is that now just substitute the values actually. Okay? Just substitute the values. So the first is going to be this, where x is Poisson distribution with this. So it's going to be e to the minus lambda 1. Okay? And lambda 1 power k divided by k factorial times e to the negative lambda 2, because y has a Poisson distribution with a parameter lambda 2, times lambda 2 power n minus k and everything divided by n minus k factorial divided by x plus y is also Poisson distribution, so it's going to be e to the minus lambda 1 plus lambda 2 times lambda 1 plus lambda 2 power n divided by what do you call n factorial. Okay, so this is what the expression that you're going to get. Now obviously these guys will cancel out. N minus k factorial and k factorial, they will also cancel out. Okay, so they'll not cancel out, but they'll get this particular form actually. So what would be the simplified version of this actually? The simplified version of this is going to be n factorial divided by k factorial and n minus k factorial times lambda 1 over, I can break this lambda 1 plus lambda 2 power n into two parts, lambda 1 plus lambda 2 power k and lambda 1 plus lambda 2 power n minus k. And if you put these together, you're going to get this actually. So lambda 1 over such a simple algebra, lambda 1 plus lambda 2 power k and lambda 1, lambda 2 over lambda 1 plus lambda 2 power n minus k. This is what that you're going to get, and this is precisely equal to n choose k. Okay, and if I call this, for example, the probability p, I give this number p, then this, so this is p power k, and this guy is 1 minus p power n minus k. Okay, where p is lambda 1 over lambda 1 plus lambda 2. Okay. Now what does this show? This shows something very interesting. This means that this conditional probability that the number of males on a given day are going to be k, given that x plus y equal to n, is a binomial distribution. So it's a PDF. So this is really a PDF of a binomial distribution. This is actually a binomial distribution with the parameters n and P any lambda 1 over lambda 1 plus lambda 2. Okay? So if we had two Poisson random variable and their sum is also Poisson, then the conditional probability that x equal to k given x plus y is n is equal to this. And actually this makes sense. So imagine there are n people, okay, so that it's like there are n Bernoulli trials in which each can be male and female, okay, so you know for each trial you have two possibilities, and we are saying that okay, out of those n, k are what do you call k are male, okay, so it's like asking in how many ways we can have k successes out of, or what are the probability that we're going to have k successes out of the n games actually. So it really intuitively meets with the Poisson binomially distributed random. Another simple quick example. So imagine you say toss a coin 3 times, okay, and you have the 2 successes out of, you know, 2 heads out of 3 coins actually. So what could be the potential outcomes? So coin is tossed say 3 times, okay, and then what we want to consider those outcomes in which you can have the 2 heads actually. So what are those potential outcomes? Head, tail, okay, head, tail, head, and tail, head actually. Okay, so these are the 3 outcomes. What we will like to prove, okay, that all these 3 orderings actually of tail and head, I mean if you see these are the orderings, so the ingredients are same, there are 2 heads and 1 tail, but they have a different order. Though they have different order, each one has an equal probability actually. Okay, so what is the probability of it? So it's going to be 1/8, 1/8, and 1/8 actually. Okay, so 2 successes with different ordering, okay, have the same probability. Now I want to do the same now with say n trials, n Bernoulli trials, okay, and k successes, and k successes, okay. Now I want to show that no matter what pattern of k successes you take, each pattern, each outcome, each what do you call ordering in which you have k successes and n minus k failure, all of these outcomes have the same probability. So in other words, I mean your first 2 successes are head and third is tail, has the same probability as that if first and third are head and second is tail actually, and it is same as this. So I want to have that, okay, imagine I now toss the coin, say for example n times, okay, and I want to show that, you know, probability of each one of such orderings in which you have k heads for example, they all, these all orderings have the same probability. Okay, this is what that I would like to show. Now let O be one of By the way, how many possibles are going to be the ordering for, say, for example, k successes? In other words, if I ask from this perspective,